Again, we're back and we will be discussing, I will be discussing a physical application of a first order, first degree differential equation. So we have the law of exponential change, or maybe termed as Noble's law. The time rate of change in a certain quantity is proportional to the quantity present at any time t. So this is applicable to exponential growth and decay problems in which a certain quantity will increase or decompose at a certain rate proportional to the amount present. Some of the problems the law is applicable are problems in radioactive decay, bacterial population growth, interest compounded continuously, and simple chemical conversion, and any other problem wherein this law may be applicable. Now, according to the law, if we have to let our Q to represent the quantity present at any time t, according to the law, the change of this quantity is directly proportional to the amount Q that is present at any time t. So, to form an equation, I introduce a constant of proportionality K. So, we have dQ dt, which is equal to a product of that constant of proportionality multiplied with Q. So, we were able to come up with a dA classified as a VSDA. So, to separate the variable, then we have dQ over Q, which is equal to K dt. Okay? So, putting my right side be 0, I transpose my K dt, and I do the integration to arrive with a general solution. So, dQ over Q minus KT, or minus K integral of dt, and that's equal to the integral of 0. So we have L in Q minus Kt, and that's equal to C. So L in Q minus Kt plus C, or L in Q equal to K times T plus C. Now, to simplify, so that our L in Q may not be present, so I can take the exponential both sides, so that is why I separate my Kt, or I associated my Kt with C. So exponential of L in Q will actually give us Q because I want to solve for a function relating my Q with the time t. So it is an exponential of Kt plus C. Under law of exponents, so we can express this in factored form of two exponential factors. We have the exponential Kt multiplied with the exponential C. The exponential C can be called as C. So my formula can be Q equal to C times an exponential Kt. But this is a general solution. What if I'm going to arrive with a particular solution by solving for the value of our C? Considering the initial condition where time is still 0, the amount of Q is still equal to the Q's of O, which is the initial quantity. So if there's an amount mentioned, then you can assign the value of your Q's of O. Okay, so when the Q is equal to Q's of O, then our T is still equal to 0. So what is your C? Your C is equal to the initial quantity. So my formula, formula which is applicable to growth and decay problem derived from the law of exponential change is equal to Q, which is equal to the initial quantity multiplied with the exponential Kt. And that will be my working equation. Q is the quantity present at any time t. The Q's of O is the initial amount present, where K is the constant of proportionality. Now, there is a bacteria culture known to grow at a rate that's proportional to the amount present. If initially there are 1,200 strands of bacteria observed in the culture, and after 3 hours, there are 3,000 strands. Okay? Question. Find the number of strands of bacteria represented with B as a function of time. The number of strands of bacteria at 7 hours. Then how many hours will it take so that there will be 6,000 strands of bacteria in a culture? Okay? Now, solution. We let our be the number of strands of the bacteria present at any time t. And by formula, So we can have B equal to, this is supposed to be Q, but since we are given B as my variable for the bacteria population, no, in terms of the number of strands, no, so I'm now changing my formula to B equal to the B sub O exponential K times T. Boundary condition, T is equal to, time is equal to 0, when time is still equal to 0, the initial quantity in terms of a unit of strands, no, for the bacteria, so we have 1,200 strands. Now, after 3 hours, it becomes 3,000. This is actually intended to solve for the value of K. Okay, so my formula can now be changed to B equal to, there's a specific amount to the B sub O, which is 1,200. Okay, exponential K times T. Now, in solving for K, we are given number of hours with the number of strands. Okay, we substitute. For our B, 3,000. And we have 1,200. So, we have the exponential K times 3. So, with your calculator, because our calculator now can solve for the value, so we can have K which is equal to 0.3054302224. The unit of time is in hours, so this is per hour. Or K may be solved by first simplifying before we take the ln. So, we have to let the coefficient of E be equal to 1. So, I have to divide 3,000 by 1, 2. So, this ratio, I can take the ln. Para if I'm going to take the ln at the right end, so this becomes 3K. Okay, so ln of the ratio, 3,000 over 1 to is 2.5. So, ln of 2.5, the ln of exponential 3K is actually 3K. So, K can be the same as what we obtained kanina. So, that is per hour. Thus, A requires us to give the function B. So, B expressed as a function of time. So, there is initial amount and there is now a value of our K. So, kompleto na siya. Our formula is now provided with the initial and the value of our K. Now, about the letter B. After 7 hours, so once you have the formula, then you substitute the value of your T to the formula, then we can solve for the B value. Okay, so substituting 7 to T. Okay, so there I obtain 10,179.07 strands of bacteria after 7 hours. Now, in letter C, how many hours will it take so that the number of strands of the bacteria is 6,000 strands. Okay, so meaning there's a value of B, which is 6,000 strands, and then we are required to solve for the number of hours from the initial. Okay, so 6,000 for our B, the formula. So 1, 2. So what is left as the unknown is T or T. So we have T, which is equal to 5.27. Okay, so you may solve this directly from calculator, or you can simplify now and take the ln both sides. You can arrive also with the value of our T. A certain radioactive material is known to decompose, no, at a rate proportional to the amount present. After 60 minutes, it is observed that 15% of the material is decomposed. No? So if 15% is lost, it means there is 85% of the initial that is left. Okay, now find the percentage remaining after 3.5 hours. No? Our unit in time, one is expressed in minutes, the other one is expressed in a unit of hours. No? So, have them be expressed in a uniform unit, either minutes or in hour. Okay? So, the time required for 30 minutes of the material of the original amount to decompose. Then, what is the half-life of the material? Okay, so letter Q, anyway, kung may nag-mention, no, there is no mention of the variable to be used. No? If that is a radioactive material, you are free to use R if you like, but I may go back to the original variable, no, used in the derivation of formula. My Q represents the amount of radioactive material present at any time T. Okay, so my formula can be Q equal to the Q sub O exponential KT. So I need to have my K. There is no mention of the initial quantity, so I can just leave my equation or my formula be expressed in terms of the Q sub O. Initial amount, Q sub O. No initial amount mentioned, so which means I am free to express my formula in terms of Q sub O. Now, t after 60 minutes or 1 hour, okay, so I'm expressing this in 1 hour because this is also in 1 hour. Okay, so that is equal to 85% of the Q sub O. Because our formula refers to the amount that is present. And if 15% is decomposed, meaning there is still 15% that is left, 85% that is left. 15% is decomposed. Or that is 0.85 of the initial, which is the Q sub O, correct? Okay. Solving for K. Okay, so if 1 hour is the value of your T, and my Q is 0.85, I can substitute to my formula, the derived formula. 0.85, the Q sub O can be eliminated. I have 0.85 and this is exponential K. So my K, if you take the ln, so there I obtain a value. Okay, .1625 okay, per hour. So my Q is equal to, so just replace your K with the specific value being calculated. So that can be your working formula. It is not being asked in the problem, but we need to have this, no, in order to solve, no, continue solving in A, B, and C. So again, you are asked to have your Q after 3.5 hours. And I have a formula already. So I can change my T with 3.5. There I have 0.562 Q sub O. Or in percentage, we can write it as 56.62 by multiplying with 100% of the Q sub O, or the initial. The time required for 30% of the original amount to decay. So, we are asked to give the time elapsed, no? When 30% is out, so meaning 70% is left, or 0.7 of the initial is remaining. Okay, now, with the formula we obtain, now, which is this one, now, complete with the value of your K. So, I can have the 0.7 Q sub O, then the Q sub O will be out. Okay, then I can obtain my number of hours, which is 2.19 hours. Okay, so try to maybe use your calculator to calculate this, or maybe try to simplify in order for you to arrive with the required T. Now, what is meant if it mentions half-life of the material? This is the time needed for the material to decompose half of its initial amount. So that also means that our amount present is also 50% left. No? So 50% decomposed, and there is still remaining amount of the material, now, which is 50%. So that is the half-life of the material. Okay, we need to know when will it be, or I need to know the number of hours needed in order that there is there is a half-life of the material that's attained. No? Okay, so in the formula, okay, I can have that as 0.5 of the Q sub O. Okay, the Q sub O is out. We have 0.5 and the exponential of. Okay, so negative for your K, then times T. So, solving for T, okay, so there I have 4.27 hours as my answer. So, that completes with the discussion with the topic and the exponential growth and decay problem. So, governed with the snowball's law or the exponential rate of change. Okay? So, thank you for watching. Okay, bye-bye.